Today we are going to be taking a look at probes for the oscilloscope, and specifically a differential probe from Micsig. Now, if you don't know what a differential probe is, don't worry. In this video we're going to cover the differences between a normal probe and a differential probe. We'll explain the types of applications you should be using a differential probe with, and then at the end of the video we're going to set this one up with my oscilloscope, show you it in action, and actually show you why you should be using one. Now, just before we jump into the video, I'd like to thank both Telonic Instruments and Micsig themselves. Telonic supplied both the oscilloscope and arranged for the probe to actually get to me, and Micsig actually arranged for Telonic to send me the probe. If you're interested in getting yourself some new test equipment, please do check out Telonic's website. There's a link to it in the description of this video, and they hold a wide range of stock from Rigel, Siglent, and many others. If you're interested in this differential probe, I'll also put a link to Micsig's website in the description of the video as well. Okay, so the first thing we're going to do is explain the difference between a standard probe and a differential probe. Now, a normal oscilloscope probe has two connections. You have your center, which is your signal read, and then you usually have this little earth clamp. Now, if you take the probe itself, the center pin goes in, it goes through a small resistor and capacitor, which is in the handle, and that then goes all the way down to the center pin on the BNC connector, which plugs into your scope. The earth connector is directly connected with no circuitry all the way down the line, again to the earth connection on the probe. And when your probe is actually connected on your scope, so if I actually just clip him on there, this earth connector is now directly connected to all of the earth points on the front of the scope, but it's also then referenced to the earth point on the mains plug on the back of the scope. And that means anything you touch with this earth connector is referenced to the mains reference earth of your property. And when you are measuring things like DC voltages on battery devices, this really isn't a problem. However, when it comes to measuring things with AC or things that are plugged into your mains, even if it's got a mains adapter, things can get particularly dodgy, and you could have the potential of either blowing your scope up or causing yourself serious damage. And this is where a differential probe comes in. Rather than the signal just being straight down through the little resistor and capacitor into the scope, it's actually isolated in the probe, and then that signal is then passed on to the scope, but it is not physically connected to the signal you're measuring. Further to that, the earth probe on the differential is actually isolated from the earth on the scope, which means it is not mains referenced. So even if you were to test it with a multimeter from here to the back of the scope, it would not show a signal. Now, I will explain this a little bit more in a minute when we take a little look at slides. There is actually a number of reasons you might want to use a differential probe, and many of these are directly related to the name of the probe itself being differential. And basically, the probe is able to measure a difference in signals between its two inputs. So whereas a normal probe is measuring between earth on your scope and the center connection, the differential probe is actually measuring the difference between the two inputs. Then that means you're actually able to measure things in a different way than you would normally be able to do it. As I have already said, you are isolated from the mains, but further to that, you can actually use the probe singly. So rather than actually use it with both connections, you can probe as a single probe. You can use it for measuring high frequency signals or very low amplitude signals as well. Common application for using a differential probe is actually working on mains power supplies. And whilst you don't have to have one, it is something that is highly recommended unless you are extremely experienced or you know exactly what you are testing is fine to test. Because again, the point to remember is this earth pin is referenced to your mains reference at your home because of the connection right through to the scope itself. Now, what we'll do is dive into a couple of slides just to try and explain this in a little bit more detail. We have our scope in the center, which is plugged into the mains. And as I'm showing here, our mains plug earth goes to our normal plug sockets, and that is connected to the earth as part of your electrical supply. Now, just to simplify it, I've got it coming down to the earth point on the transformer, but depending on what your home electric system is, it might be attached to neutral or whatever. However, the basic important premise to understand is the earth point on the back of the scope via the 3-pin lead is connected to the earth in your home. If you then take a look at the other side of the scope, we have our probe connected with the center pin going into our single input, and then the earth pin to the 3 connections. Now, these 3 connections is connected to this earth point over here, because that is how the oscilloscope is actually wired up internally. And whilst there are some oscilloscopes that do have isolated inputs, the vast majority of oscilloscopes do not. So anything you touch with this probe here is referenced the same is your earth over here. Now, when you are working on battery devices, things like an Arduino, a battery product, and you're testing signals and voltages, the reality is wherever you clip this probe really doesn't matter too much, because you are only referencing that device to the earth of your property. This device is not plugged into the mains. It is not got its own potential in relation to the mains, so there is nothing to be concerned about. Now, just showing the demo circuit of this, the reality is we have a battery powering the Arduino. We're testing a signal off the IC, and because there is no reference between this battery and this mains, because the earth probe is connected to the earth shield in here, everything is fine, because there is nothing to link this circuit back to our main circuit or our mains transformer. Now, if we wanted to test more complicated devices, or specifically power supplies and devices that are connected to mains, things get a little bit different, and you have to be very careful on where you're putting your probe. For instance, if we were to take this circuit here, this is a pretty much standard switch mode power supply. Again, our oscilloscope is connected to mains via earth, but this time our power supply is connected to earth as well. And what you can see here is we've got our probe connected to this lowest point here, which is actually earth. And we're then testing the voltage across the top of this point up here on the transformer. Now, this is actually okay, because this area here is earthed via the connection to the mains. This is all earthed, so it is one circuit all at the same reference, and we would not have a problem. However, we may decide we want to measure the circuit in a different place and move our earth probe up to here. Now, if you had a basic understanding of the power supply, you might think this is okay to do, because you've got your FET transistor here, which is switching it on and off, and that's actually going down through the resistor to ground. So when the transistor's turned on, that would be ground. Therefore, I would be perfectly safe to measure that signal here. Now, the reality is, though, this isn't safe, because whilst you might think, okay, we've got our switching transistor here, which is going down to earth, and when it's turned on, it's passing the circuit through. When the transistor's turned off, this whole section of the circuit sits at mains reference live voltage. And then your reality is you're actually putting your circuit here at mains reference voltage. That is connected to earth, and the reality is you would get either a very big bang, you could burn your scope out, or you could do yourself a massive amount of damage. Now, this is where a differential probe kicks in. The differential probe actually isolates this input from whatever you're measuring. This device acts as the go-between between your scope and the circuit you're measuring. And whilst again we do have that circuit connected in the same place, if we look at it, there is actually a stop here to prevent this connection reaching the BNC connector on our scope. And actually you could measure that point without a problem at all, and actually take a reading from it to be able to see the transistor in action. But it is something that you can only do with the differential probe, because it is putting that block in between the circuit you're testing and the scope itself. Now, whilst that is quite a basic overview of the reasons for having a differential probe, it covers the main aspects of it. Now, something I haven't actually mentioned in this video is something called a mains isolation transformer. Now, whereas the differential probe isolates your scope from the product you're testing, a mains isolation transformer isolates the device you're testing from your main circuit at home. And instead of it being directly connected, it actually goes through the transformer and isolates the device as well. Now, from a safety point of view, when you're testing things like power supplies, you really should be using both a differential probe and a mains isolation transformer as well. It really isn't one or the other. It really should be both. In this video, we're only talking about the differential probe, but you really should also consider a mains isolation transformer as well. And that is something I will cover in another video in the future. So the next thing we're going to do is take a dive in and take a look at this differential probe itself from Micsig. Now, when you get it, it comes in this nice hard plastic case, which means you're able to carry it around with you, and it's also well protected as well. When you open the case up, you will find inside a whole host of parts. You get the differential probe, as well as some additional probes and some cables as well. Now, the probe itself, as you can see, is quite a bit bigger than a standard probe on an oscilloscope, but that is because it has all of that isolation circuit built in. Looking around it, on the base, we have our input for our BNC, and you will notice that there is a USB port, and this is a 5-volt USB port for powering the probe itself, because it does need power to actually be able to work. Now, they do include a USB cable with it, and for me, I was able to simply plug the USB in and plug it into the front of my scope, and that powered it absolutely fine. On the side, you then have a USB-A port for passing through, and then on the top, we just have our 2 probe inputs, just as we would expect. Now, on the front, you will also find a ×50 and a ×500 button. This is exactly the same as you would find on a normal probe, and it's just the scale for setting what input you're going to be testing. Now, this probe allows up to 1000 volts in 500 or 150 volts in ×50. So you do need to make sure that you do have it set correctly. And if you are doing that, you do need to make sure your scope is set correctly as well. Otherwise, you won't have the correct input value showing. Other than the USB and the 2 buttons on the front, that is everything you need to know about it. It is made from nice hardware in plastic, which means it will last and it will take the odd knock as well. And it really is as straightforward as that. Now, also in the kit, as I've shown, they also give you a couple of extra probes as well. You get these nice grip-on probes here, which you can clip onto various components. You get a traditional style probe as well, with our normal cover, and then they actually give you some croc clips as part of it as well. Now, the model on this one is the DP10013, and that is the actual model number of the one we're going to be using here. Now, the next thing we're going to do is actually get it all plugged in and then show you it in action on the Rigel oscilloscope itself, and we're actually going to take a close look at it measuring a switching signal on a power supply. Now, something I do want to add is if you are doing anything like this, please do be very, very careful. Switchmode power supplies specifically can have some extremely high DC voltages as well as AC input as well. The reason for having the differential probe is to add an additional layer of safety. However, that does not mean you can just go prodding about and nothing bad will happen. You do still need to be very careful at what you're doing. And as I've already mentioned, you really do need to be using a mains isolation transformer as well. The next thing we're going to do is demo the differential probe looking at a switch mode power supply. Now, as I have already said, please do make sure that you are being careful if you are doing anything like this. Now, the first thing we're going to do is take the probe and connect it onto our channel 1 on the scope. We're then going to take our USB plug it into the front of the scope into the port, and then plug that into the differential probe itself. The next thing we're going to do then is turn on the scope, allow it to actually boot up, and then we're going to check that we've actually got our probe settings correct, depending on what option we're going to use on the front of the differential probe, and we'll take a look at that as soon as it boots up. As you can see, it's all turned on, and we've got our 2 input options on the front of the differential probe to choose. We've got times 50 or times 500. Now we're going to be measuring a switch mode power supply with about 200 to 300 volts DC. Times 50 allows up to 150 volts, so we're going to want to make sure we are on times 500. Now we then need to make sure that the scope is on the correct input too, so we're going to tap channel 1, we're going to click our probe option, and we're then going to select times 500 from the list for that one, so it knows the input is correct for the scaling. Now just to demo, the probe is actually working before we do some testing. I've got it clipped onto the 1 kHz oscillator. We are still on 500 input, so you can see that the display is showing up. Now if I changed it to times 50, we could then simply change the probe input if we wanted to, because this is a much smaller signal. We've not got to worry about that. Click that to times 50, hit auto, and then you will see a much cleaner version of that signal kick in, because whereas before we were actually doing it on the times 500, it's heavily boosted, whereas now we're on the times 50 because voltage wise we're actually only at 1, 2, 3, 4, 5, 6, and it's on 500 millivolts, so it's about 3 volt. Whereas if we move it over the times 500, change the probe input to times 500 as well, click auto, you will see that it will rescale the input, and again it will show it in 1 volt increments, so we are looking at 1, 2, 3 volt signal in total. Now the next thing we're going to do now is get this hooked up to a switch mode power supply, and we're going to measure 2 specific areas. We're going to measure the switching output off the driver IC before it gets to the MOSFET, and then we're going to measure the MOSFET as well and show you that on the display to have a look at a working switch mode power supply and how it actually displays with the differential probe. So I now have my probes set up on the switch mode supply on the input to the FET. So this is the signal from the control IC within the switch mode element of the supply that is driving the FET, which drives the transformer. Now, as this is on the input to the FET, this is actually a lower voltage end of the circuit. It's about 42 volts, 39 to 42 volts. So I currently have the probe set on times 50 for this, which is below that 150 volt recommendation for the times 50. As you can see, the signal is about 99 to 100 kilohertz, which is then at a period of 10 microseconds and about a rise of 5 microseconds. And as I said, it's hopping around the 40 to 42, 45 volt area. Now we'll next jump in and measure the signal from the FET to the transformer. Now this is a high voltage DC signal, so we will then need to switch the probe over to that times 500 mode from that times 50. Otherwise we will actually get a flashing red light on the probe to tell us that something is wrong. We're now on the output of the FET into the main transformer, and as you can see, it is showing the waveform on the display, and the first thing to notice is the voltages involved. We are talking 500 to 600 volts DC here, much higher than we were seeing measuring the input to the FET. We are now in times 500 mode on the probe as a result of that. Now this is the dangerous end of the supply, and whenever you are measuring something like this, I've said it before, I've said it time and time again in this video, but you need to be extremely careful. Now as you can see, the switching is happening at 90 kilohertz. It is peaking at a max of around 600 volts, and you can see that the period again is 10 microseconds. Now what we have here is the actual switching of that FET transistor on and off. So if I scroll out, you can see it there, or if we scroll in, you can see it much more clearly when we're looking at it that way. Now the thing to remember about this is this signal will change as the output of the supply changes. This is a battery charger, and it actually regulates the output depending on the draw of the battery as the battery is progressing through its charge, and this would actually change as that current draw changes as well. But what we can see here is that our switching transistor is doing exactly what we would expect it to do. Now the point I'm measuring this at is between ground and the output of the FET. The thing to remember with that is what you're actually doing is seeing it the opposite way around. When the transistor is off, you are getting the high voltage, and when the transistor is on, it is then shorting it down to ground, because remember, the signal of the transformer is actually being allowed to pass through to ground when the transistor is activated. When the transistor is off or the FET is off, then the signal actually raises up to that high voltage, and that's why we're seeing the peak. So what you're seeing is that transistor, or that FET transistor, switching on and off very, very fast due to the signal from the IC that is controlling the switch mode supply. And that is it for this video. Now, finally, I just want to stress again, whenever you are working with mains referenced products, be extremely careful. Whilst the differential probe is an additional layer of safety, it cannot protect you from everything, and you do need to be extremely careful of when you are working on anything with high levels of AC or DC voltage, specifically power supplies. Though the differential probe is something that you do need to have if you are doing it regularly, alongside that mains isolation transformer too. Now, if you have found this video useful, please do consider hitting that subscribe button. Also, put any comments you'd like to share in this video too. I will check them out. Finally, I'd like to thank Telonic Instruments and Micsig. This video would not have been possible without their support. There are links to them in the description of this one as well. If you're after any test equipment, please do check them out too. Today's video is sponsored by us. If you find it interesting, please do check out some of our other content. Hit that subscribe button and don't forget to hit the little bell and select all. That way you'll get updates on any new videos we release in the future. We also have a brand new dedicated live streaming channel. Sunday evenings, 10 PM UK time, I go live on this channel talking more drones and tech. It would be fantastic to see you on the stream. There's a link to that channel in the description of this video as well. Please head over there, hit the subscribe button and the bell as well, and I look forward to seeing you on the stream. Finally, if you'd like to support the channel, please do check out some of the links in the description of each video. These are affiliate links, but the income from these does allow us to keep buying products to be able to talk to you guys about on the channel in the future.